while you rest peacefully in your bed, high above your head, beyond the clouds and the atmosphere we breathe, lies an invisible graveyard. A place where objects created by humanity wander eternally, trapped in a silent orbital ballet. We call this ghostly collection space debris. Each fragment, each piece is an object that once had a purpose, a function, but now simply exists, spinning around our planet at unimaginable speeds. Imagine for a moment. More than 36,000 large objects, bigger than a soccer ball, have been carefully catalogued by dedicated scientists. They know the trajectory, the speed, the size of each one. But that's just the tip of the visible iceberg. Beneath this layer of traceable debris lies a hidden universe. More than 1 million coin-sized fragments, tiny metallic souvenirs from past missions, floating in precise and relentless orbits. And if we could narrow our perspective even further, we would find something truly extraordinary. 130 million microscopic particles, smaller than the nail on your little finger, each traveling at 28,000 kilometers per hour. It's a speed so extreme that it defies our everyday understanding, faster than any airplane, any rocket in the atmosphere. At that speed, even the smallest fragment becomes a devastating weapon, capable of destroying entire satellites with a single impact. The International Space Station, that shining jewel of human engineering that orbits serenely above our heads, is well aware of this invisible danger. Regularly, like a skilled dancer avoiding obstacles, the station must perform delicate maneuvers, burning precious fuel just to deflect fragments that could pierce its shields. For the astronauts inside, even a sliver of just 3 millimeters, smaller than an ant, represents a real threat, capable of piercing metal and compromising vital systems. The highest concentration of these ghostly debris is in low Earth orbit, that region of space between 200 and 2,000 kilometers in altitude. It is precisely there, in this vital zone, where thousands of satellites operate, providing communication, navigation, and weather forecasting. It is a busy space neighborhood, but also dangerously polluted. Where do all these fragments come from? The story is fascinating and, at times, tragic. Most of this space debris originated from violent explosions, old rocket stages that, decades after completing their mission, exploded in the vacuum of space, scattering thousands of pieces in all directions. Residual fuel, old batteries, pressurized systems that couldn't withstand the extreme conditions of space. Each explosion adds hundreds, sometimes thousands of new fragments to the orbital inventory. But there were even more dramatic events. In 2009, something unprecedented happened. An American satellite from the Iridium constellation collided head-on with a deactivated Russian satellite, Cosmos. It was the first accident between two intact satellites. The impact generated more than 2,000 new fragments, each following its own chaotic orbit, creating new dangers for future missions. Imagine the silence of that moment. No sound, just two objects meeting at absurd speeds, instantly shattering into a cloud of twisted metal. But this event, however significant it may have been, was overshadowed by a deliberate decision. In 2007, China conducted an anti-satellite test, purposefully destroying its own Fengyun 1C weather satellite. It was a demonstration of military capability, but it also created the largest debris generation event in space history. Thousands of fragments were instantly added to the already problematic orbital inventory. Fragments that will remain there for decades, perhaps centuries. The most disturbing thing about this whole scenario is that there are objects so tiny that we simply can't track them. They exist, they're out there, traveling at lethal speeds, but they're invisible to our most sophisticated monitoring systems. A simple sliver of paint detached from an old rocket can, at those extreme speeds, pierce the hull of a spacecraft. Size doesn't matter in the vacuum of space when traveling at 28,000 kilometers per hour. And there's something curiously human about this whole story. Among the millions of cataloged fragments, there are objects that tell more personal, more intimate stories. Tools lost by astronauts during spacewalks have joined this orbital graveyard. Astronaut Piers Sellers, during a maintenance mission, accidentally lost a spatula, a simple work brush. That object, which fit in the palm of his hand, became an improvised satellite, orbiting the Earth until it eventually burned up in the atmosphere. Even more memorable was the 2008 incident when astronauts lost an entire toolbox during an outer spacewalk. Imagine the scene. In the absolute silence of the vacuum, surrounded by the black immensity of the cosmos, that white toolbox simply slipped, floating slowly away. For a time, it was the brightest unmanned object in the night sky, visible even from Earth with good binoculars. A toolbox orbiting like a small accidental satellite, until gravity and the thin atmosphere finally caused it to descend and disintegrate. Metal plates, nuts, bolts, pieces of broken solar panels. All these mundane items make up the inventory of near-Earth space. Objects that in our daily lives would be discarded without a second thought have become lasting threats in the orbital environment. Anti-satellite weapons tests, conducted by various nations over the decades, have transformed functional satellites into clouds of fragments. Each of these tests is a demonstration of technological power, but also a permanent contribution to the growing problem of space debris. There is, however, a consolation in this story. Most debris does not remain in orbit forever. Slowly, almost imperceptibly, the thin atmosphere at lower altitudes exerts a subtle drag on these objects. Over time, their orbits decay, they lose altitude, and eventually plunge back into Earth's atmosphere. Most burn up completely during this re-entry, becoming momentary shooting stars that very few people notice. On average, about one piece of space debris per day re-enters the atmosphere, most being small fragments that disintegrate completely, posing no risk to those below. It's a continuous cycle. We launch objects into space, they fulfill their functions, eventually become debris, and slowly, over years or decades, return to the planet that created them, burning silently in the upper atmosphere, leaving only a very brief luminous trail against the night sky. Take a deep breath. Let these images float through your mind like debris in space. There are more stories to come. When we think about numbers, sometimes they lose their meaning. But try to visualize this. 170 million fragments smaller than a centimeter. Each one an individual particle with its own orbit, its own speed, its own destiny. It's as if we've created a second ring around the Earth, not of ice and rock like Saturn's rings, but of metal, plastic, and ceramic, remnants of our space ambition. These tiny particles, some no larger than grains of sand, carry devastating kinetic energy. Think of an ordinary grain of sand, the kind you find on the beach, harmless between your fingers. Now imagine that same grain traveling at 28,000 kilometers per hour. At that speed, it transforms into a deadly projectile, capable of piercing complex space equipment, destroying delicate electronic systems and compromising missions that cost billions. Our relationship with space debris is, in fact, as old as our own presence in space. Since 1957, when the Soviet Union launched Sputnik 1, that silver sphere the size of a basketball that emitted a simple beep beep as it orbited, we began to leave our mark on the cosmos. Sputnik itself eventually fell, but it started an unintentional tradition. Each mission, each launch, would leave something behind. The geography of this orbital graveyard is not uniform. There is a specific region, a particular altitude, where the concentration of debris is denser and more concerning. It is low Earth orbit, that band that extends from a few kilometers above the atmosphere to about 2,000 kilometers in altitude. There, in this vital zone for telecommunications, Earth observation, and manned flights, is where we find most of the fragments, the dead satellites, the lost pieces. It is also where the International Space Station performs its orbital ballet, and where its occupants need to remain constantly vigilant. Several times a year, the ISS needs to fire its thrusters or receive a push from an attached cargo spacecraft, just to avoid threatening objects. Flight controllers on Earth continuously monitor, calculate trajectories, and assess risks. When an object larger than 10 centimeters gets too close, when the probability of collision exceeds certain limits, orders are sent, engines are activated, and the entire station, with its hundreds of tons, ascends or descends a few kilometers, enough for the debris to pass harmlessly. Now imagine something even smaller, a single screw. Perhaps it came loose during the assembly of a satellite, or perhaps it was ejected during an orbital explosion. This screw, weighing only 1 gram, less than a coin, travels at more than 28,000 kilometers per hour. At that speed, it carries enough energy to cause catastrophic damage. It's as if every tiny object in orbit were a microscopic cannonball, perpetually in motion. NASA, the institution that took us to the moon and beyond, dedicates considerable resources just to cataloging and monitoring this growing problem. More than 35,000 objects larger than 10 centimeters are registered in its databases. Each one has a unique identifier, a known orbit, a history. Technicians track these objects daily, updating their positions, predicting their trajectories. It's a Sisyphean task. The more we monitor, the more we discover. And when we look at those historically responsible for this situation, 3 nations stand out: the United States, Russia, and China. Together, these space powers created the vast majority of orbital debris. Not necessarily out of malice, but as an inevitable byproduct of decades of space exploration, militarization, and commercialization. Let's return to that dramatic moment in 2009, when the 2 satellites collided. One was American, part of the Iridium constellation that provided global communication. The other was Russian, Cosmos, already deactivated for years, merely drifting silently. They met over Siberia, at an altitude of almost 800 kilometers. The impact was catastrophic, instantaneous, silent. More than 2,000 new fragments were created in that instant, each now following its own elliptical orbit, some rising, others descending, all representing new dangers. But it was China in 2007 that set a grim record. In an anti-satellite test, they deliberately destroyed their own Fengyun 1C weather satellite. The satellite disintegrated into more than 3,500 trackable fragments, and likely millions of smaller, untrackable pieces. It was the largest cloud of debris ever created by a single event. These fragments are still there, still pose threats, and will remain so for decades. The longevity of these objects in space is astonishing. Depending on the altitude, some debris can orbit for centuries. The higher you are, the thinner the atmosphere, the less drag, and the slower the orbital decay. Objects above 1,000 kilometers in altitude can remain in space for thousands of years. Think about it. A screw lost today at that altitude will still be orbiting when future civilizations look to the sky. But there is good news amidst the gloomy ones. Most of the debris that eventually returns to Earth poses no danger to us down here. The atmosphere acts as a protective shield, a natural incinerator. When an object re-enters, friction with air molecules generates intense heat, thousands of degrees. Most debris simply vaporizes, turning into bright plasma for a few seconds before disappearing completely. And to this day, despite decades of objects falling from the sky, there is no confirmed record of any death caused by space debris. It is a testament to the vastness of the oceans and uninhabited areas of the planet. When we analyze the tracked space debris, we discover something interesting. Approximately 70% are not whole satellites, but fragments, pieces of things that were once complete. Debris from collisions, pieces from explosions, chips from smaller impacts. It's like an archaeologist studying ruins, but these ruins are still moving, still evolving. Europe, through its space agency, recognized the gravity of the situation. They created an entire team dedicated exclusively to orbital prevention and cleanup. Scientists and engineers are working on innovative technologies, space nets, harpoons, lasers, solar sails, all designed to capture, slow down, or redirect hazardous debris. It's a cosmic cleanup mission, an attempt to remedy decades of orbital pollution. Even iconic objects are not immune. The Hubble Space Telescope, that magnificent observatory that revealed the depths of the universe to us, that photographed distant galaxies and spectacular nebulae, suffered an impact in 2021. A tiny fragment, traveling at extreme speeds, collided with one of its solar panels, leaving a micro-hole. The telescope continued to function, but that small scar is a reminder. Nobody is completely safe up there, and what is perhaps most worrying, many of the objects contributing to the problem are not even debris in the traditional sense. They are dead satellites, complete, intact, but without function. They ran out of fuel, their batteries died, their systems failed. Now they are just masses of metal and electronics, perpetually orbiting, posing enormous risks because they are large, dense, and more likely to be involved in catastrophic collisions. Some experts paint grim projections. Without intervention, without cleanup technologies, without changes in how we conduct space activities, near-Earth space could become unusable within a few centuries. The most valuable orbits will become so congested, so dangerous, that new satellites will be unable to operate safely. It would be as if we had locked the door to our own space future. And there's an even more terrifying scenario, one that scientists call Kessler syndrome, named after the NASA consultant who first described it. Imagine a chain reaction. A collision generates fragments. These fragments collide with other objects, generating even more fragments, which collide with more objects, and so on. In a matter of decades, Earth would be enveloped in a dense cloud of debris, making near space completely inaccessible. Satellites would be destroyed, Manned missions would be impossible. Our ability to explore beyond Earth would be cut off. It would be as if we were building our own orbital prison, surrounding our planet with the remnants of our ambitions. Close your eyes and visualize our blue Earth, enveloped not only in white clouds, but in an invisible ring of metallic fragments, each telling a story of conquest and consequence. Among all the objects that silently wander above our heads, one stood out for its enormity. Imagine, more than 8 tons of frozen metal and fuel, an entire stage of an old Soviet rocket abandoned decades ago. It was the size of a bus, perhaps larger, slowly spinning in a vacuum, a gigantic relic of the space race. This orbital monster represented a danger not only because of its size, but because of its mass. The larger and heavier an object, the more devastating any collision would be. The International Space Station, our permanent outpost beyond the atmosphere, intimately knows the delicate dance of orbital survival. On average, between 1 and 3 times a year, it needs to move. Not by choice, but out of necessity. Controllers in Houston, Moscow, and other control centers identify an approaching threat, calculate the probabilities, and make the difficult decision to burn precious fuel to raise or lower the station's orbit, avoiding a potentially catastrophic encounter. But there was one particularly tense moment, one that tested the nerves of everyone involved. In 2021, Russia conducted an anti-satellite test, destroying one of its own old satellites. The explosion created a massive cloud of fragments that dispersed rapidly, some of them on trajectories dangerously close to the ISS. The astronauts on board received urgent orders. Seek refuge in the emergency capsules. For hours, they remained there, prepared for an emergency evacuation if necessary, while the cloud of debris passed. It was a visceral reminder of how vulnerable we are up there, of how a single political decision can put lives at immediate risk. Think again about those tiny objects. A nut, a bolt, perhaps a washer. Objects you would find in any toolbox, completely harmless in your hands. But in space, accelerated by gravity and the absence of air resistance, they can reach speeds exceeding 25,000 kilometers per hour. At that speed, a bolt weighing a few grams becomes a hypersonic projectile, capable of penetrating the hull of a spacecraft like a knife through paper. There is a specific region of near space where the problem is particularly acute. Between 700 and 1,000 kilometers in altitude, there is an extraordinary concentration of debris. At that altitude, atmospheric drag is almost non-existent. Objects there can remain in orbit for centuries, perhaps millennia. It's as if we have created a permanent ring of garbage around the planet, an artificial layer that future generations will inherit, whether they want to or not. Low Earth orbit, that vital band where we operate most of our satellites, is the most critical and the most polluted. It's where we find not only the largest debris, but also the most dangerous microscopic particles. Grains of cosmic dust, metal shards smaller than a pinhead, each traveling at unimaginable speeds. Even these tiny particles can puncture solar panels, damage optical sensors, and compromise critical systems. The Hubble Space Telescope, that magnificent observatory that revolutionized our understanding of the universe, bears on its surface the scars of decades in space. Its outer casing, its panels, have been repeatedly struck by micrometeorites and small debris. Each impact leaves a small crater, a permanent mark. During maintenance missions, astronauts observed hundreds of these small craters, each telling the story of a high-speed encounter. The physics of orbital collisions is brutal. The average impact speed between debris is 10 kilometers per second, about 36,000 kilometers per hour. At these speeds, it doesn't matter much whether the object is solid or liquid, hard or soft. The kinetic energy is so immense that everything behaves almost like a fluid at the moment of impact. Metal vaporizes. Composite materials disintegrate instantly. Even something as mundane as peeling paint poses a real danger. Imagine, over the years, exposure to intense sunlight, extreme temperatures, and the vacuum of space causes the paint on satellites and rocket stages to begin to peel. Tiny flakes, no larger than snowflakes, break off and begin to orbit independently. And these paint particles, traveling at orbital speeds, can cause surprising damage. In the 1980s, the Space Shuttle Challenger, before the tragedy that would make it famous for sad reasons, had one of its windows damaged by a simple piece of paint in orbit. The impact created a small crater in the multi-layered glass, compromising its structural integrity. The window had to be replaced upon its return to Earth. It was a reminder. In space, there are no truly harmless objects. Currently, about 34,000 objects larger than 10 centimeters orbit our planet. It's an impressive inventory, each item catalogued, monitored, its trajectory constantly updated. But beneath this visible layer of large debris, there exists an invisible universe. More than 128 million fragments smaller than a millimeter. They are so small that they cannot be tracked individually, but they exist in astronomical numbers, a haze of metallic particles enveloping the planet. The Mir space station, that Soviet outpost that orbited Earth for 15 years, eventually had to be decommissioned. In 2001, it was deliberately guided back into the atmosphere, where it disintegrated over the Pacific. But before that, throughout its operational life, it generated tons of smaller debris. Pieces of thermal insulation, fragments of solar panels, particles of oxidized metal, all gradually breaking off and remaining in orbit. And the irony is that each new launch, each new space mission, inevitably adds more debris to the orbital inventory. Even when everything goes perfectly, without accidents or failures, small objects are released. Metal clips that hold payloads come loose during stage separation. Protective covers are ejected. Residual fuel is vented, instantly freezing into small crystals that become debris. It's the inevitable cost of doing business in space. But not everything remains up there forever. Most debris that returns to Earth meets a dramatic and terminal end. Atmospheric re-entry is a violent process. Friction with the air generates temperatures of thousands of degrees Celsius. Most objects simply incinerate, turning into vapor and plasma. But larger, denser objects can partially survive. Studies suggest that between 20 and 40% of the mass of a large object can resist re-entry and reach the surface. However, there is a growing movement to actively address this problem. Private companies, taking advantage of the commercial revolution in the space sector, are developing missions dedicated exclusively to orbital cleanup. These are ingenious concepts. Satellites equipped with robotic arms to capture debris, propulsion systems to push dead objects back into the atmosphere, even ground-based lasers to slow down small fragments. It is the birth of a new industry, space cleanup. Europe, in particular, is at the forefront of these technologies. Engineers at the European Space Agency have developed prototypes of a space net. literally a giant net that can be launched from a Hunter satellite to capture larger debris. It's like space fishing, but with targets moving at 8 kilometers per second. The technical challenges are immense, but the initial prototypes have shown promise. And occasionally, very occasionally, pieces of space debris that survive re-entry touch the ground. Fragments of fuel tanks have been found on remote farms. Pieces of dark, twisted metal have appeared in backyards. High-density metallic spheres have fallen into oceans. So far, miraculously, there are no confirmed records of direct injuries caused by these fragments. Earth is vast. Oceans cover most of the surface, and truly uninhabited areas are extensive. The probability of a specific object hitting a populated area is incredibly small, but not zero. There is a region of space where objects are truly eternal. It's the geostationary orbit, that precise band at approximately 36,000 kilometers altitude, where satellites appear fixed in the sky because they rotate at exactly the same speed as the Earth. At this high altitude, atmospheric drag is non-existent. Any piece of space debris that reaches there can remain for thousands of years, perhaps tens of thousands, orbiting silently while entire civilizations are born and disappear on the surface of the planet below. And let's return to that sliver of paint we mentioned earlier. Imagine a particle of just 1 millimeters, virtually invisible to the naked eye, smaller than a human hair. Now accelerate it to 28,000 kilometers per hour. At that absurd speed, this microscopic particle can pierce the glass of a satellite, compromise spacecraft windows, and damage delicate optical sensors. It's a perfect demonstration of how, in space, speed transforms the harmless into the deadly. To monitor this orbital zoo of dangerous objects, humanity has built a global surveillance network. More than 50 radars and telescopes around the planet constantly point to the sky, tracking, cataloging, predicting. It's a silent international effort. Stations in the United States, Russia, Europe, Asia, all sharing data, all working to maintain an up-to-date inventory of what's up there. These systems operate day and night, in all weather conditions, like vigilant sentinels protecting our orbital assets. The International Space Station, throughout its operational life, has performed more than 30 evasive maneuvers. 30 times, the occupants felt that subtle nudge when the thrusters fired, raising or lowering the orbit just enough to avoid a catastrophic encounter. Each maneuver is preceded by hours, sometimes days, of careful analysis. Flight controllers calculate probabilities, assess margins of error, and make decisions that can mean the difference between safety and disaster. When we look at the distribution of space debris, we find that approximately 70% of it is concentrated in low Earth orbit. This makes sense. That's where most space activity takes place. Earth observation satellites, space stations, crewed missions, all operate in this accessible and relatively inexpensive region. But it's also where the risks are greatest, where the density of objects makes each launch a careful navigation through an orbital minefield. And when we investigate who is responsible for this situation, 3 names repeatedly emerge: China, the United States, and Russia. Together, these space powers have created the vast majority of the debris now orbiting the planet. Decades of military, scientific, and commercial launches have left their permanent mark on near space. Some of the debris up there are true historical relics. There are fragments from missions carried out in the 50s and 60s, at the dawn of the space age. pieces of rockets that carried the first satellites, remnants of Cold War experiments, components of missions that very few people alive today remember. These objects are like archaeological artifacts, but instead of being buried in the ground, they perpetually circulate above our heads. When a rocket explodes in orbit, whether due to system failure or pressure buildup in unvented fuel tanks, the result can be catastrophic in scale. A single explosion can generate up to 3,000 distinct fragments. Each explosion transforms a large object into a cloud of smaller projectiles, multiplying the problem exponentially. It's like breaking a glass. Instead of one large object, you now have hundreds of sharp shards, each dangerous in its own way. Among the cataloged objects, approximately 2,200 are abandoned rocket stages. These metallic cylinders, some the size of school buses, were used to propel payloads into space and then simply left there, without fuel, without control, just drifting. Many still contain residual fuel, remaining pressure, and batteries that are slowly degrading. They are orbital time bombs, waiting for the moment when they will spontaneously fragment. And there are surprisingly mundane objects among the cataloged debris. Nuts, bolts, screwdrivers, even gloves lost by astronauts during spacewalks. It's almost comical to imagine. A work glove designed to protect human hands in extreme environments now orbits eternally as a small accidental satellite. Each of these objects has a story, a specific moment when it slipped from gloved hands and began its solitary orbital journey. In 1965, astronaut Ed White, the first American to perform a spacewalk, accidentally lost a tool during his extravehicular activity. That simple tool remained orbiting the Earth for months, occasionally visible through ground-based telescopes, until eventually its orbit decayed and it burned up in the atmosphere. It was one of the first demonstrations of how objects lost in space don't simply fall, but remain, circulating indefinitely. NASA, in its conservative estimates, calculates that there are about 500,000 untraceable fragments smaller than a marble. These particles are too small to be detected by radar, but numerous and fast enough to pose real threats. It's like navigating through an invisible hailstorm. You know the particles are there, but you can't see them until it's too late. Recognizing the growing gravity of the situation, the international community developed specific guidelines. The Space Debris Mitigation Guidelines is a code of conduct for new space missions, establishing best practices to minimize the creation of new debris. Satellites should be designed to deorbit at the end of their useful lives. Rocket stages should be passivated, their batteries discharged, their fuel tanks vented, to reduce the likelihood of future explosions. These are sensible rules, but since they are not legally binding, their adoption depends on the goodwill of the nations and companies involved. And there is an insidious danger that many fail to consider. Deactivated satellites can spontaneously explode. Over the years, batteries degrade, electronic components fail, and residual fuel tanks can build up pressure due to solar exposure. Suddenly, without warning, a satellite that has been dead for decades can violently fragment, creating hundreds of new pieces of debris. It's a chemical and mechanical time bomb, and dozens of these potentially unstable satellites are silently orbiting right now. That historic 2009 collision between Iridium-33 and Cosmos 2251 continues to reverberate. The more than 2,000 fragments generated in that impact are still there, still pose threats, and will remain so for decades. Each of these fragments has its own orbit, its own period, its own inclination. It's as if that collision created a permanent swarm of orbital projectiles. The sad reality is that virtually all space launches, even the most successful ones, leave some kind of residue. Clamps that secure payloads, protective sensor caps, stage separation adapters, all are designed to be ejected at some point during orbital ascent. It's the unavoidable cost of doing business in space, but a cost that is accumulating dangerously. But there is hope on the horizon. Private companies, driven by both idealism and commercial opportunities, are developing innovative technologies. SpaceX, known for revolutionizing access to space, is researching methods to deorbit its own Starlink satellites in a controlled manner. Astroscale, a Japanese company focused specifically on debris removal, is developing satellite hunters, small robotic spacecraft designed to approach, capture, and deorbit specific debris. These are the first steps in a new space industry: orbital cleanup and maintenance. Up there are pieces of missions that no longer exist as active programs. Fragments of the Soviet space program, remnants of satellites from countries that changed their names or ceased to exist, components of space agencies that were dissolved or merged. They are orbital ghosts, echoes of past ambitions, still circulating decades after their creators ended their activities. To put the energy of these impacts into perspective, a fragment of just 1 centimeter, traveling at orbital speeds, carries kinetic energy equivalent to a car traveling at 100 kilometers per hour, colliding head-on with a concrete wall. Think about that for a moment. An object the size of a small coin has the destructive power of a serious car accident. It's brutal, unforgiving physics. And we return to that grim prediction with which we have become familiar. Without proper control, without active intervention, the amount of space debris could render near-Earth space unusable for decades, perhaps centuries. It would be as if we had polluted not only our oceans and our atmosphere, but also the space immediately surrounding our planet. The most valuable orbits, those that give us global communication, precise GPS, and climate monitoring, could become so dangerous that new satellites could not operate safely. It would be a self-inflicted blockade of our own space future. Let these thoughts float gently through your mind. There are immense challenges, but also human ingenuity working tirelessly to find solutions. Space calls to us, and we are slowly learning not to pollute the next ocean we sail. Let's return for a moment to the International Space Station, that permanent outpost of humanity floating silently more than 400 kilometers above our heads. Throughout its operational life, it has already had to perform more than 30 special maneuvers, each a reminder that space is not the tranquil void we imagined, but a dynamic and increasingly dangerous environment. Each maneuver burns precious fuel, consumes astronauts' working time, and adds stress to the station's systems. But the alternative, remaining in the path of an approaching piece of debris, is simply unthinkable. The scale of energy involved in these orbital collisions defies our everyday intuition. A fragment of just 1 centimeter, smaller than your fingernail, can release energy equivalent to a hand grenade when it collides with a satellite. Think of what a grenade does to a building, to an armored vehicle. Now imagine that destructive power concentrated in a split-second impact, all kinetic without explosives, just the brutal physics of extreme speed transforming a small piece of metal into a devastating weapon. It is this absurd speed, an average of 28,000 kilometers per hour, that makes orbital cleanup so complex. You can't simply cast a net and expect to capture something moving that fast. It would be like trying to catch a bullet with a baseball glove. Conventional technologies simply don't work at that energy and speed scale. Each proposed solution needs to take into account not only capture, but the precise matching of orbital velocities, something that requires sophisticated engines and extremely precise control. Currently, more than 36,000 objects larger than 10 centimeters orbit our planet, each catalogued, tracked, and with their trajectories constantly updated. It's an impressive inventory, maintained by networks of radar and telescopes around the globe. But these are only the objects large enough to be seen. Just below this visibility threshold lies an even more worrying population. Approximately 900,000 fragments, ranging from 1 to 10 centimeters, orbit completely out of control. These are, paradoxically, the most dangerous. They are too small to be tracked individually, but large enough to cause catastrophic damage. A satellite can avoid detected large objects, but there is no defense against this invisible multitude of medium-sized projectiles. It's like navigating through a minefield where you can't see the mines. And beneath this layer lies the microscopic universe. More than 128 million fragments smaller than a centimeter. It's a haze of metallic particles, an artificial atmosphere of debris that completely envelops the planet. Every launch must traverse this layer. Every satellite must operate within it, accepting occasional impacts as an unavoidable cost of doing business in space. When we examine the historical responsibility for this situation, 3 nations dominate the statistics: Russia, the United States, and China. Together, they are responsible for more than 75% of all orbital debris. Decades of space competition, orbital militarization, anti-satellite testing. All of this has left permanent marks on the near-space environment, and the process of creating debris can be alarmingly fast. When a satellite explodes, whether due to system failure or weapons testing, it can instantly generate thousands of fragments. An intact object transforms in milliseconds into a cloud of hundreds or thousands of independent projectiles, each following its own slightly different orbit, gradually spreading out over the following months and years. The most frustrating thing about this whole situation is that the technology to begin cleaning up space already exists, at least in its basic forms. We can build space-hunting satellites, develop capture systems, design methods to deorbit debris. The problem isn't primarily technical. It's political, economic, and legal. Who pays for the cleanup? Who takes responsibility for debris created decades ago? How do we regulate the removal of objects that may still contain sensitive or classified technology? These are complex questions that the international community is still trying to resolve. Meanwhile, most retired satellites simply continue orbiting. Without fuel to maneuver, without batteries to power systems, they drift silently. Dead objects among the living, posing increasing risks with each passing year. Some will remain there for decades, perhaps centuries, depending on their orbital altitudes. But the system has a natural, albeit slow, cleaning mechanism. Debris re-enters the atmosphere almost daily. Most are small fragments that burn up completely before reaching the ground, turning into momentary shooting stars that very few people notice. It's a constant cycle. New debris is created, old debris falls. But unfortunately, we are creating it faster than we are losing it. Approximately 200 objects re-enter the atmosphere each year, either in a controlled manner, when space agencies deliberately guide deactivated satellites back, or naturally, when atmospheric drag finally overcomes orbital speed. Controlled re-entries are carefully planned to occur over oceans, far from air routes, minimizing any risk to people or property. And occasionally, very occasionally, substantial pieces of space debris survive re-entry and touchdown. Fragments of rockets have fallen in Brazil, partially burning but leaving twisted metal pieces on remote farms. China has seen empty fuel tanks from rocket stages fall in rural areas. Australia has found pieces of old satellites in its vast interior. Each incident is investigated, the fragments analyzed, their origins traced. So far, miraculously, there are no confirmed records of deaths caused by these impacts. But the real risk isn't that the debris will fall on our heads. The far greater, far more immediate danger is that debris will collide with other debris, creating more debris, which will collide with even more objects, initiating an uncontrolled cascading effect. It's an apocalyptic scenario for the space age, a future where the very success of our space activities prevents us from continuing those activities. Kessler syndrome, named after NASA consultant Donald Kessler, who first described it mathematically in 1978. He calculated that once the density of objects in certain orbits reaches a critical point, collisions would become inevitable, each generating more fragments, which would cause more collisions, in a chain reaction that could last for decades or centuries. Some orbits would become completely unusable, surrounded by dense clouds of debris traveling in all directions. The Chinese weather satellite Fengyun 1C, destroyed by a missile in 2007, perfectly exemplifies the problem. More than 3,000 trackable fragments were created instantly, and probably tens of thousands of smaller, untrackable fragments. It was a demonstration of military capability, but also an event that pushed some critical orbits several steps closer to that Kessler tipping point. And then came the first truly accidental collision between intact satellites. In 2009, Iridium-33, an active and functional American communications satellite, collided head-on with Cosmos 2251, a deactivated Russian military satellite. The impact occurred over Siberia at an altitude of almost 800 kilometers. It was completely silent, totally invisible from Earth, but absolutely catastrophic for both objects. This unique collision generated over 2,000 cataloged fragments and countless smaller fragments. Instantly, the density of objects in that specific orbital region increased dramatically. Each of these new fragments represents a new threat to other satellites, a new chance of future impacts. It is exactly the type of event that Kessler predicted, and now we know that it is not just theory, but demonstrable reality. But there are signs that we are learning. Some modern satellites already include planned self-destruction systems, designed to self-destruct in a controlled manner at the end of their useful lives. Not catastrophic explosions that generate thousands of fragments, but careful disintegration that minimizes the creation of dangerous debris. Or, even better, systems that allow the satellite to deliberately deorbit, plunging back into the atmosphere where it will burn up safely. And there are truly futuristic proposals for dealing with smaller debris. Space towing projects that use high-powered terrestrial lasers to heat them slightly, creating a small force that, over weeks or months, gradually alters their orbits until they fall naturally. These are beams of light transformed into space cleaning tools, gently pushing objects that are hundreds of kilometers away. It's technology bordering on science fiction, but it's being developed by dedicated teams of engineers around the world. Prototypes are being tested, simulations are being refined. Each small advance brings us closer to a future where we can not only explore space, but keep it clean, sustainable, and safe for future generations. Take one last deep breath. Let these 100 stories settle gently in your mind like cosmic dust. The space above us is vast, mysterious, and now we know it is also surprisingly full, not just of stars and planets, but of the metallic echoes of our own ambition. It is a story of conquest and consequence, of problems created and solutions forged. As you close your eyes and drift off to sleep, imagine our Earth seen from afar. That beautiful, fragile blue and white sphere, now enveloped in an invisible ring of fragments. But also imagine the engineers working, the scientists calculating, the new technologies being developed. We are learning, slowly but surely, to care not only for our planet, but for the space around it. Good night. Sleep well. The stars continue to shine, and tomorrow we will bring more order to the cosmos that surrounds us.